I had misplaced my trusty eraser, needed some room. I want to say a few more things about this table before moving on to another example, and we might even drill one more on video, one of a different size. First things first, I derived the expected values, the expected frequencies associated with each of the inner cells in the table with this sort of an appeal to intuition, and it's clear, I know from vast experience that not everyone has that intuition. So before moving along from this one, although it'll become more explicit and obvious in the next one, I did want to illustrate how you do it physically. So if you don't have the intuition, in a simple problem like this, just use the formula. Saw this in larger form. I'm abbreviating now. Row marginal times column marginal divided by sample size explicitly. So we're going to wonder about the expected value for this particular cell on the table. So once you're here, we're going to find its column marginal and its row marginal. Multiply these times each other. 50 times 50 is 2,500. 2,500 divided by sample size of 100 is 25. And that works in each cell of the table. Second, more about critical values, and in particular about 0.05, and a head start on working on this stuff in class using R over here. This is how simple this problem is to work. In R, the data equal matrix, and this is a C, open parent C. It's all be on one line. And then you're just defining what's in the matrix. The observed value is 3020, so it's working like this: 3020, and 2030, right? Telling it that it has 2 rows and 2 columns. And then you can do the chi-square test by just typing this, chi-square, it's CHISQ dot test, open parent data, close parent. What you're going to get if you do that, interestingly enough and unfortunately for R, but you're going to get that instead of 4, which is what we saw last time. Chi-square equals 4 because we added across all the cells, 1 plus 1 plus 1 plus 1. What you're going to find if you just type data from R is you're going to find a chi-square equal to 3.24 with a p-value not less than 0.05, but a p-value instead of 0.072. What I have a little subscript here. I don't know if you can see it. It's Y. That stands for chi-square with the Yates correction. Don't worry about what that is. Actually, if you worry about what that is, Google it. Find its Wikipedia entry. The Yates correction. Something I don't use, and there are a couple of technical reasons why you might not want to. I have the subscript P here for Pearson. That refers to Carl Pearson, the mathematical statistician who developed the chi-square, developed a lot of things, as we'll see, in statistics. This is called Pearson's chi-square, the one that we calculated physically in the just previous video. It's Pearson's chi-square, and it is equal exactly to 4, and you could find that in R by, instead of typing data, type data comma correct equal capital F. That's going to turn off the Yates correction and give you Pearson's chi-square. But note, and there's something really illustrative here. Note that we're talking about a correction that I'm suggesting oftentimes is trivial. Actually, it's not so trivial as it is the Yates correction sometimes is too big. And so I just avoid it usually. But look at the difference it would make if we're the strict constructionist on frequentists, as a frequentist, and saying sort of 0.05 is the cutoff level. 0.072 is above 0.05. So by that strict construction, we don't have a statistically significant result here if we apply the Yates correction. If we don't, we do. That makes no sense, and yet too much of empirical social science is still governed in this way. What I want you to take away from this is, from the frequentist perspective or any other, I want you to take away the sense that you're getting a sort of empirical estimate of the degree of uncertainty associated with making a statement about there being a gender gap from only 100 observations. This is a very significant result substantively. It's big empirically. If you look here, you see three and 5 females are Obama supporters, 3 and 5 males are Romney supporters. That extrapolated into the population would be a gigantic and very, very substantively significant result. And that's not sort of focusing on. We're using these not to make exact sort of judgments, or we shouldn't be, about statistical significance and establishing a cutoff point. We're realizing we only have 100 data points, and we're constrained in what we can do simply because we have only 100 data points. And yet this particular relationship is so profound that in spite of that, we find with Pearson's chi-square a value of 4, which has associated with it a p-value less than 0.05, meaning that 95, approximately 95 times in 100. If we did this again with a simple random sample of 100, we would get a result much like this. We're going to move on. Again, this is a head start on in-class work. If you run this, we're going to do several of them in class. I'm going to do another one on another video of a different size to illustrate the degrees of freedom differences and how it varies, degrees of freedom, how they vary across tables of different sizes. More next time.